This work is, I think the title describes well what we are trying to do here. We're trying to come up with a policy that emulates the round-robin policy, which is known to have very nice features in terms of sharing of resources across multiple users or files that are coming into the system in the case of a server setup. So we want to generalize that to the case of a wireless network with fading. So this is led by Bin Lee. So I'm kind of, he could be the one to present, but he couldn't come here, so I'm just covering. So here's the motivation. In the space of scheduling algorithms, when you have many clients trying to share, in the case of the wireline setup, say a web server, which provides a constant amount of service at a given time, but you got to share it across these users. The scheduling algorithm is deciding how to share this constant amount of service across these incoming traffic, which come and go. So there's a dynamics to these, demands. Round-robin scheduling in that context is widely used and also has very nice features in terms of fairness and insensitivity. So what happens here is the flows, or so-called file requests, are coming and they're served in a sort of cyclic fashion, okay, until they're done and they just leave the system. In that respect, each flow that's in the system at the time gets the same amount of service, and it's kind of shared through this cyclic fashion. So where one packet from each flow is served during the service instance. So I guess what I mean by that is given by the animation. You have these multiple flows with different sizes, and you get to serve one at a time in some cyclic fashion, and keep going that way. So nice properties of round robin are it's essentially fair in terms of sharing the time and the service accordingly across the active flows. And in the case of the wired server setup, a single server setup, it's work conserving, and so it achieves maximum throughput. And it has this insensitivity to the size of the file. So, and that's the key, aspect that we care about also in the wireless setup, where the mean response time or delay of a request depends only on the size of the file, the mean size of the file. So that's very attractive because longer files take longer, shorter files take shorter, and therefore there's this insensitivity to the size of the other files in the system, right? So it only depends on the size of the file itself. And this is hard to prove. It's like non-trivial to prove, and it resides on these kind of results across a longer time frame. The question is, does there exist a policy, scheduling policy, that applies to the wireless setup, especially where you also have fading involved? So this is the question. So we just changed this previous model where we now have a wireless network with fading. So I'll be more clear about what we assume there. Okay, so the application could be many, and a few of them are depicted here. It could be in the context of IoT applications, where you have increasingly many devices want to access a common or multiple resources in an environment. You would potentially have a large number of these. They will have traffic coming in to be served, and they may have different sizes. So how do we deal with these traffic dynamics and the fading states of the channels that they might observe, and the sizes of the files? So that's the motivation. You could also have applications in the larger scale on the environmental monitoring. The solution that we propose is motivated by round robin, where we ideally want to do this in a periodic fashion. So we want to schedule them in a periodic fashion, but it also has to be adaptive because, we don't know which files will be there beforehand, so we have to do it in an adaptive fashion. and emulate the round robin in this context. So there's some work related to this question. Some of them are concerned with the fully connected networks, like a base station setup where everybody is sharing a common environment, where these extend upon the round robin-like policies. But this is only like in the fully connected setting. There are more general network topologies which does not account for fading possibilities. A variety of works, some of which are listed here. They have different focuses from, in some cases, from ours. Say, for example, the first looks at maximum fairness rather than the metrics that we are interested in. There are works on CSMA-like policies, but doesn't do much of a round robin. And also TDMA-like policies, but doesn't account for traffic dynamics. So incoming traffic is not accounted for. It's assumed that you have always something to send. So there's also a group of works that generalize the processor sharing to wireless networks that are listed here, but they require knowledge of the capacity region you're dealing with. And then implementation is very hard because of that, the assumption of that knowledge and choices made based on that knowledge. There's some work on age or delay-based design. So these are looking at how long the file has been in the system, and based on that waiting time, tries to make decisions on who to serve next. There's one group of work here that does it using, that does the analysis based on fluid limit arguments, which does not generalize easily to the case that we will look at. And there's another work that we had previously at Infocom last year, where there's a Lyapunov-based design, or analysis of age-based design, and which we proved the throughput optimality using that. But here, again, the focus is based on ages, and the delay insensitivity property that we alluded to before does not really work well with this kind of policies. I'll show at the end. And there's some other works by these people, including our earlier work, that have some relevance, but we will note kind of there's some crucial differences too. Okay, so what is the model? So we assume a fading model of this channel states. We will assume on-off fading here. So it's assumed to be IID over time with the Bernoulli distribution. In terms of notation, let's say Ci of t is the fading state of link I at slot t. Okay, so links keep on fading this way. There's wireless interference in a multi-hop environment. This would look like this. There will be collisions if two packets go and they have a common receiver. There will be collisions, but you can have successful transmissions if they're far enough. So an interference model is in that sense a link and tension-based model. And we will denote S with S the set of feasible schedules we can select at the time, right? So that wouldn't interfere with each other. So this is an abstract model of collision-based interference. So again, going back to our goal, we have these files coming in with their different file sizes to these nodes, but then they are assigned to links. So think of these queues per link. Links fade, and we got to do these scheduling decisions over time with non-interfering schedules in each case. We have an assumption of a maximum number of files that can arrive to a link at a given slot. So that's AI max for the ith link. And the goal is to develop this round-robin-like policy. Also, another assumption is the maximum number of packets in a file, which could be high, but then there's this maximum that we assume will be the limit, and there's a positive probability that you will have that big size file coming in. So those are the technical assumptions, some of which I think are relaxable, but for our current argument, we make these assumptions. So how do we run this round-robin-like policy in this general context is driven by this use of this metric we call time since last service. So this is a metric we introduced before and analyzed, but with additional add-ons to it. Now we're just purely looking at this metric, which is much challenging on its own. So the way this metric works is for each file, in the system at the time, say file J, there's a counter. And that counter is keeping track of how much time has passed since we last served a packet from that file. Okay, so that's the metric. It's not the age of the file, it's not the whole time it's been in the system, but it's just the time since it received the last time it received service. And its dynamics is given by this. So it's incremented by 1 whenever there's no service given to that file in the last slot, or it's set to 0, so it kind of sharply decays to 0 if there's a service to it. So it has this sort of behavior, which is not a very smooth behavior, obviously, right? It increments smoothly, but then sharply decays. So it doesn't have these nice queue-like dynamics that we can use in fluid arguments. So this kind of policy, using the time since last service, actually, in the case of the single service system, easily reduces to running a round robin. This is one way to get a round robin policy working, where suppose you have these 3 files at time 0, suppose their initial time since last service is set to some number, but let's take it to be 0. It could be any arbitrary number. You serve one of them, its time since last service is remaining at 0 because it just received service. The others are incremented. The next time slot, you choose one of the others as the largest to be served according to this rule. And well, that would reset it to 0, and the others are incremented. Now the next one will be in line at number 2, and then that puts them in an order. So the following round, you can go back to the highest one, set it to 0, and the others are incremented, and keep going that way. And so that naturally has this behavior of cyclic service of the files in the system, right? So it reduces to this in the case of argmax tj. It would be true for any other function of tj that's increasing, right? Not just the tj, but any other function that is increasing in tj. Okay, so that's good. So it reduces to that. Now we want to run an algorithm using tijs for the general wireless, right? So that's the policy, basically. So the policy makes scheduling decisions based on trying to maximize this linear summation of the weighted sum of these functions of tijs. So these functions I'll explain a little more, but the tijs are the key metrics. So there's they are the measure of how long it has passed since last service. And then depending on the channel state at the time, the scheduling decision is to be made to maximize this linear summation. So that is the policy we want to analyze. For the functions choice, we have to make a technical assumption about what the function class has to be. It's an increasing function, and it has this property that for any k and b, the function value evaluated at k times x plus b is upper bounded by f of x plus some constant c. That kind of functional form is satisfied by logarithmic sort of functions. So in the examples I'll talk of, I'll take the f to be a logarithmic function of the time since last service, where the technical assumption is more generally this. So what it does is it basically within each link, whenever a service is to be given for that link, you just serve the file that has the largest time since last service. So you just serve the one that has been waiting for the longest since its last service. And how to choose the link to activate is governed by this f value evaluated at the maximum for that link times the link quality captured by the on-off state, right? So this is the kind of a split of how to serve within a link and how to choose the links to serve. Okay, so implementation could be done in a simpler way through this multi-layered system setup where you have a transport layer and a MAC layer. So whenever a packet is served for a file, it leaves the MAC layer and the next packet is pushed into that MAC layer. So actually what we're looking at is the time since last service metric is nothing but the age of these packets at the MAC layer once they enter the MAC layer. So this is another way to implement the policy by this notion of transport versus MAC layer waiting times. So the main result is showing the throughput optimality of this policy. Okay, so the policy emulates round robin, is expected to have nice properties of round robin in the wireless context, but the main technical result is that this policy is throughput optimal to start with. That's the basis, which itself is not that easy to prove because the policy that we're having doesn't have queue-length dynamics that are governing it. So these fluid limit analysis that was used before for age and stuff don't apply. We have to take a different way of proving it. Essentially, the way the proof goes is through two steps. The first step has to do with relating this function, in general, in specific case, the logarithmic function of the ti max, that's the weight of the link, with the maximum age at that link. So instead of this time since last service, we want to relate to the age metric. Age is the waiting time of that file, of the files at that link. Okay, so not just the time since last service. So, and then using our earlier work that has to do with the age-based design, to use a sort of novel Lyapunov function, nothing like a quadratic, but quite different Lyapunov function, to show that, you know, this connection between the T and the W allows us to prove actually the system is throughput optimal. So the details are, of course, have to be skipped, but the essential point for this to show the first step is trying to come up with upper bounds and lower bounds on this common metric that looks at the number of files at the link I at slot T as a function of the Ti max on the one side, Ti max is the time since last service metric, and the waiting time on the other side. Okay, so these upper and lower bounds relate the Wi to Ti and helps us make this argument on the relationship between the two. And I'll kind of leave it at that. And the second step builds on the earlier analysis where we did this age-based design with that sort of novel Lyapunov function choice. And kind of combining these two gives us the throughput optimality result. Okay, so what about these, now that we have this policy and the throughput optimality, we want to understand further nice properties of the algorithm. One of them is the short-term fairness. Short-term fairness is something to do with the variability of the inter-service times. So from a packets or files perspective, what you care about is periodic service, right? The periodicity of service is something desirable. And the variance of the inter-service time, therefore, is one way to figure out how much variability you see in this schedules that you see, like the service times that you see. That's normalized with the mean squared of the inter-service times. We can make a connection between this metric and the expected time since last service metric that we introduced. So that's a nice connection, allows us to look at this to talk about that periodicity property. Okay, for our policy, what we did in the simulations is to look at two cases of fully connected networks on the one side, with fading, and a switch case, 3x3 switch case for the other setup. So these two setups is fully connected and not fully connected setups. And in both cases, our interest has to do with how the file size, the change in the file size, affects the performance. Two metrics are of interest, I guess. One of them is the mean file size that's coming into a link. And the other has to do with the burstiness of those. The burstiness is governed by this, the probabilities here. So you either get a large file of size m with a probability and one otherwise. So you have either short or big files. And the burstiness is the m that's governing the variance of this file size. So first thing we did is to confirm the throughput optimality result we analytically proved, but then we also looked at the case where the choice of the function is not even logarithmic, it's even some other choices, in particular the linear. So in both cases, the on-off fading case, we have the, obviously, stability. And in the other case, we also observe stability, which we should for the logarithmic choice, but we also get that for the linear choice of the function. So that's sort of interesting. We don't have a proof of that. There's no proof at this point showing this policy with a linear function actually is throughput optimal, but seems to exhibit such properties, at least in these setups we looked at. The further questions concern comparison to other policies that exist. Okay. The two policies of interest are, one of them is what we call queue-length based scheduler, although this is not the traditional max weight It's slightly different. It's based on this work of Kaderi and G and Shrikant. What it does is it chooses the links by using the maximum weight on the logarithmic function, again, of the number of files at the link. So the number of files, not the content of the files, but the number of files in the link is the weight, and its logarithm of that number is used for the max weight decision of which links to activate. Okay, so and once you choose the link, it still does the round robin like scheduling of files in that link. Okay, so that's the way this policy works. So it has a round robin embedded into it, but its choice of links is governed by the number of files at the link. The other one is the age-based scheduler. This does, again, with a logarithmic mapping, it looks at the maximum age of the files of each link as the weight. So the link here, the weight here of each link is the maximum age of the files at the link, and then within it does this round robin. So there is a round robin nature to both of these, but then it's both different from what we do, because in our case, we choose the links based on the logarithmic function of the time since last service, the longest time since last service, instead of these other metrics. So to look at the comparison, and just to make the note, I guess, if we use the traditional max weight-like policy, it will really perform poorly in terms of the metrics we are interested in, so we didn't do that comparison. These are the more fair comparisons, we thought. So here the x-axis is the burstiness of the files. So as the burstiness of the files increase for a load of some 0.9 in this case, what we do see is that our policy, the time since last service, for both the setting of the this is for the average delay performance, so it's very insensitive to this burstiness metric. And the Q-length based one is also quite insensitive to it. The age-based one is more and more sensitive as the burstiness increases. So the burstiness comes with large delays for some of the files, and that large delays affect the link scheduling, and therefore has an effect on, more effect on the age-based design. It doesn't have as much of an effect on the Q-length based because it just looks at the number of files. It doesn't look at the number of packets, but just number of files, so it seems to be insensitive just as ours is. Ours does still better than the Q-length based one throughout these burstiness levels. And in terms of short-term fairness, the difference is even bigger in the age-based one. So age-based one is a lot more affected by the variability of the service times or inter-service times as highly affected by the age-based design. So insensitivity seems to be exhibited through the example. This is done for the fully connected network. In terms of the slowdown, which is the metric of file delay divided by its size, yes. So this was the insensitivity property of round robin I started with initially. So it's measured by, the ratio of time you spent on the file based on its size. So it's division of the file delay by the size. It's, again, we see very insensitive behavior throughout the higher burstiness for both of the policies, but TSLS-based one is still better throughout. We, again, did the same for the 3x3 switch case. We also did, in this case, the case of linear choice of functions. And logarithmic choice and linear choice, they both exhibit very nice behavior. The Q-length base also is flat, but then if you use the linear function for the Q-length base, it seems to have more of an impact on its performance. So that's kind of an interesting observation there. And finally, we did this for the 3x3 switch case. Again, we did the comparison of the linear, logarithmic of these three policies. The age-based one is out of the picture, basically. Q-length and the time since last service compete throughout, and time since last service is generally better in the cases we have, all the cases we have looked at. So to sum up, I mean, this objective here was to come up with a round-robin-like policy. We did it through the use of this metric, time since last service, which has these sharp changing behavior. Analysis of it is harder because of that dynamics. So we're able to prove throughput optimality of it, and we were able to observe the other insensitivity and slowdown properties that are favorable to these other comparisons. Things to prove, obviously, are those properties in more rigorous sense, which itself was tough to do in the wireline server case, so it'll be challenging, but that at least we have promise of the policies exhibiting those properties, so we'll kind of attack those next. So with that, I conclude. Thank you.